about direct detection, indirect detection, accelerator, switching the diagrams. We'll have a full week next week about direct detection. You heard a bit already of indirect, and we'll hear a little bit more of indirect. And today is the talk on the accelerator production by Eduardo Pontón from IFT. Thanks.
Thank you very much. So let me start by thanking the organizers for an excellent school and, of course, for the invitation to give this lecture. As Martin already said, so this one should be thought as part of the series that was given by Fabio and Farinaldo, just to cover one last aspect of the dark matter field. Okay, let's hope it's not a problem. So very quickly, the outline of this talk, basically there are three parts. I will start by making some points in introductory remarks. Then I will discuss a bit in generality the issue of models and the role they play when you try to interpret results. And in the third part, I will turn with a few examples, which I hope will illustrate where we are and what we can do. The question of dark matter searches at colliders. So just to re-emphasize something which is, so you already saw in the previous lectures, but it's always important to be aware of this, is that the evidence we have for dark matter comes from very different sites, different scales, different times in the evolution of the universe. And altogether, we have a rather consistent and simple picture of how all of this fits together. Okay, so we have, in particular, when we're talking about dark matter, we know it's there, and we have some ideas about how to think about that based on this simple picture. But there are many things. So, in fact, actually, maybe I should say one of those things that we normally assume, and it's a rather natural assumption, is that the dark matter component of the universe corresponds to some sort of degree of freedom, some particle similar to the particles we have seen. But we also know that it cannot be one of the particles we know about. Okay, so we're talking about new physics if we're thinking in this way. And in that context, there are many things we would like to know and we don't know about this, the identity of dark matter. Basically, we don't know anything about its mass, spin, is it stable, very basic properties. We don't know how it interacts with things except gravitationally, which of course, well, first of all, just theoretically we know that things interact gravitationally, but it's also important that that's how we know that it's actually there. But there are other things that are open questions, okay? And one of the, so if we are lucky, looking at collider experiments could provide a way of accessing some of these, the answers to some of these questions. Let me now turn to this diagram that I'm sure everybody has, or most likely most people have seen before, and probably some of you have seen many times before. I want to spend a couple of minutes here just to, since this is a school, to say a few things explicitly, which are often left unsaid. So this diagram, so first of all, it tells us that we're talking about two worlds. We have the world we know about, the standard model particles, and there is some dark matter, which is something different, something we don't know exactly what it is, okay? Implicit here also is the fact that these two worlds interact in some way. Now, of course, we know already that at least that happens gravitationally, but usually what we have in mind here is a bit more than that. And in fact, when you start thinking about how you can what you can imagine dark matter could be, it's quite natural to imagine that these two sectors can interact in some ways. The diagram can also be read in different ways. And that, at some level, reflects a deep statement about our understanding of the description of elementary particles based on quantum field theory. Namely, if you have some fundamental interaction vertices between particles of this sort, there is a distinction between those vertices, those fundamental interactions, and the actual physical processes that you can consider. Meaning that for the physical processes, you have to think also about what are the initial and the final states, okay? So here, for example, given some interaction that connects these two sectors, one can imagine that you prepare your initial state with two dark matter particles, and this tells you that they can go into standard model particles. So that's an annihilation process, which in many cases is relevant when you think about how dark matter came to be, when you think about the relic density, something that I think you have seen in previous lectures. So that's reading the diagram from right to left. But you can also read it from top to bottom, for example, in which case you have an initial state with the dark matter and the standard model particles, and they can basically scatter elastically into the same kind of state, okay? Or finally, reading from the left to the right, one can start with two standard model particles and do something physically very different, which is to produce the dark matter particles, okay? Now, at the same time, this diagram allows us to describe in a very succinct way how we approach the subject in a practical way. So, for example, again, starting from the right to the left, so the annihilation processes are the processes that one is interested in when one is thinking of looking for dark matter indirectly. In other words, dark matter is everywhere. From time to time, it will annihilate into standard model particles like this, and then you hope to see those products, right, when they arrive here on Earth. Or from top to bottom, one has everything that falls under the umbrella of direct detection. Namely, we have dark matter particles here or wherever the experiment is, and you wait until these particles interact, in practical cases, with nuclei, and deposit some energy, and you hope to be able to see that. And then from left to right, you can produce dark matter particles, in principle, by starting, say, from beams of standard model particles at an accelerator, which is the subject of this lecture. So, okay, so we have that very nice and appealing picture. But at the same time, one should be aware that you should be a bit careful in the interpretation of the things I just said. Because in practice, perhaps those correlations I'm talking about may not be quite observable. And the issue here is that this diagram is a bit too schematic. So for example, when we write here SM, standard model particle, it really can be many particles. We know there are many degrees of freedom in the standard model. And the standard model particles which are relevant for the different setups that we just described can be different. So for example, if you're thinking about indirect detection, starting with dark matter annihilation into something, typically you will be interested in annihilation into things that somehow stand out and you can hope to see them. Or for example, one important case is if you produce photons at the end, because they can travel long distances and come to us, and perhaps we can see them. Or, okay, sometimes you can produce things that don't travel as easily, but perhaps they have certain characteristics that allows them to distinguish them from other sources of production of these particles. So that's the case, say, of antiparticles like positrons, antiprotons, for example. If you are talking about indirect detection, then, as I already said, you're interested in interactions between certain heavy nuclei and the dark matter particle. For the collider side, coming from the left, let's say at the LHC today, we have proton beams, so that's your initial state. So it's somewhat different, but at first sight, not so different from the nuclei in direct detection. But actually, in many cases, as when you start thinking about examples, it can happen that the way to get from this side to the right side could be quite convoluted. You could first produce other things and end up producing dark matter later on. So in practice, these three processes can be not necessarily so easily correlated with each other. Okay. In addition to that, and this is particularly relevant for the collider story, the dark matter side itself may also refer to different particles. Okay, not only because what's out there may have different components, which is a possibility, but also because it can very well be that it is not only that type of particle, but that this comes accompanied by other states that could be more relevant for production at the collider, but that nevertheless, in the collider setting, are indistinguishable from the actual dark matter particle. So when we're talking about dark matter at colliders, you should perhaps use a quote-unquote for that. In any case, it is certainly true that having the potential access to various aspects like this is a very attractive program, and it's what one of the reasons that the area is quite interesting. So it's very active. In fact, even if it turns out that the situation is far more complicated than the simple diagram would suggest initially, we may end up thinking of that as a lucky strike. Think just perhaps you're familiar with a different case, the case of the Higgs boson. I don't know, perhaps many of you are too young, even though this is a recent effect, but this a recent event. But I don't know if you were following the thing, so a couple of years ago. And so it just happened that, so we're looking for this thing, basically excluding the presence of this state for a long time. And it remains some window in mass, the last window, the most difficult part to access, and that's where it was. So it took a while to get it because of that, and there was plenty of speculation in the meantime because we're not seeing it, etc. People are impatient. But now that we know it's there, it turns out that the fact that it's difficult to see is connected with the richness of the phenomenology associated with the Higgs boson. And that gives us a handle to investigate many properties of that state. So similarly, I would argue here, if you end up with a complicated story, that may end up being appreciated as an opportunity. Let me introduce some additional terminology, which is, just connected to the previous comments. So there's the concept of a portal, so something that allows you to connect the standard model sector to the dark matter sector, and connected to that, the concept of a mediator. So one imagines, one imagines something like this. One has the standard model sector, the dark matter sector, which may be a simple thing like 1 degree of freedom, or perhaps something more complicated, and some other degrees of freedom that talk to each other. So in general, one has two sorts of couplings, one coupling the mediator to the standard model, lambda SM, and another one coupling the mediator to the dark matter sector, lambda dm. And this, you can imagine situations where the dark matter talks directly to the standard model, but this kind of picture arises quite often, and so it's good to classify it explicitly. And here I'm showing just a particular example of that scheme. It's a renormalizable example where the dark matter particle chi exchanges some sort of a spin 1 degree of freedom with the standard model. Notice that when you do something like this, there are a number of assumptions that sort of go into that, and so you should try to be explicit. So for example, here I could be thinking of the chi of the dark matter as some sort of fermion, and as I already said, this mediator having spin 1, so it's sort of what the notation suggests. And that, of course, need not be the case. You can imagine other possibilities. The dark matter itself can have different spins, or even if it's a fermion, it could be either a Dirac or a Majorana fermion. But it can also have a spin 0, spin 1. So that's, as I said at the beginning, the spin is one of the open questions we have. And similarly, the type of mediator, we don't know anything about that. Okay, so there are many possibilities you can think about it. And even within that possibility, these vertices, the structure of those vertices, can take different forms which have different consequences for when you analyze some setup like this. So that's just to start warning you that there are many things that we don't know at this point. So there's plenty of possibilities. So what you end up doing is sort of classifying possibilities to try to cover and make sure that you're not leaving anything out when you look for something like this. Now, just to say a couple more trivial things, but to be sure. So when we talk about dark matter candidates, we are talking about sufficiently long-lived particles, although they could decay. So if you can have a dark matter particle that decays over, let's say, longer than the age of the universe, or sometimes when it can decay, depending on the decay products. For example, if you produce photons at the end, you can actually infer that it should live much longer than the age of the universe. But okay, we don't know if it's exactly stable or just very long-lived. But anyway, this will not be important for the collider. In fact, as I was saying at the beginning, we may be talking about other degrees of freedom that are much short-lived, but nevertheless long-lived on detector or collider timescales, and we wouldn't know from that point of view. We also know that it has to be sufficiently weakly interacting. So, for example, it should have no electric or color charges, which tells us something about what to expect when you try to produce something like this. So it will not be necessarily easy. Now, perhaps additionally, you could consider additional constraints on the couplings and the mass coming from the relic density considerations. Very often, the things you have in mind are thermal relics, and then, as you saw in previous lectures, basically the relic density is determined by its annihilation cross-section. And that gives you, in principle, some constraints on such things as couplings and mass. But of course, we should not forget that such considerations are somewhat subject to cosmological assumptions. Okay, so if you are interested in searching for it at colliders, you should not necessarily take that too seriously. So you should keep an open mind. Nevertheless, thinking about those things, in particular the case of thermal relics, is one of the main arguments for thinking that it is really worthwhile looking for these things at colliders. And the argument, which I think should have been made during the classes already, is that the relic density scales like one over the cross-section, and requiring that it be what we see tells you that this cross-section has to be of the order of a picobarn, which is the typical cross-section of electroweak processes. And more importantly, it is something that can be accessed at colliders. So we will have this sort of situation often in mind. On the other hand, there are no guarantees, of course, that we will see it, even if we have such cross-sections. For example, it could be that the dark matter just lies beyond the reach of the collider. Either it's too heavy, or perhaps even it's too light, but appears in some way where backgrounds are too large, or it's somehow difficult to see. So one could be unlucky. Or it may just be too weakly interacting. One example of that, which I believe was also somewhat covered. I don't know, Fabio, if you talked about axions. Okay, anyway, but so I will not talk about axions, but it's one of the possibilities, and which is, so you can look for axions, but you wouldn't do it at colliders. So we have dedicated methods for that. In comparison to direct and indirect dark matter searches, one important difference as compared to collider searches is that the direct and indirect searches do depend on astrophysical assumptions, for example. So in that sense, collider experiments are cleaner. So they give an orthogonal way out which do not depend on such assumptions. But on the other hand, as I already said, the dark matter sector may not be within the collider reach. And I also said already, one really cannot tell from, let's say, a discovery of dark matter at colliders that it is really the dark matter that it's out there in the universe, simply because we cannot tell that it is really stable. As long as it is sufficiently long-lived that it leaves the detector and we don't see it, but it could be decay a bit afterwards, and we don't know, right? And that's a possibility. So just to restate this, in a collider environment, the dark matter particle may or may not be what is out there filling the universe. But I will still keep it calling dark matter particle for simplicity, just keeping in mind that it may be slightly different. So let me turn to the issue of, I don't know if there are any questions. The issue of models and dark matter searches. So there are different ways in which you can think about this, but one of the important messages I would like to transmit is that it is important and somewhat unavoidable to think about models in the interpretation of results, which of course so far are all negative, but even if there was to be a positive signal, models will play an important role. And so I will just go over some, conceptually over some type of classification that is sort of settled now and affects the way that, for example, experimental results are presented and so on. So one can start by thinking of what they call here full-fledged models, so some sort of, in some sense, UV-complete models that may be motivated by reasons other than dark matter. So as you know, probably there are other open questions which may motivate theoretical investigations in certain directions, and that may end up having some connection to dark matter, but not necessarily as an input. It can be also just the implementation of elegant theoretical ideas you might be after, okay? Or even the explorations of possible worlds, which is something people have done. So a prototypical example of that kind of thing is the case of supersymmetry, as in the, for example, the minimal supersymmetric standard model, where you have reasons to introduce many new degrees of freedom, basically doubling the number of degrees of freedom that you have already in the standard model, which is quite a bit. And so you can end up expecting quite complicated processes like this. For example, the production of some color particles like gluinos, which then cascade decay, producing all sorts of particles, and towards the end producing, so these chi-1s will be what correspond to the dark matter candidate in a model like that, okay? And there are also bosonic versions in the context of extra dimensions, for example, which have a similar behavior, even though the details are different, the spins of the particles are different, and so on. But, okay, so you can have reasons for exploring certain models that are actually quite complicated, okay? In particular, they have a large number of unknown parameters because you have introduced many degrees of freedom. But normally, not all of those are relevant in the context of specific questions, like if you're interested in dark matter. Still, even if you sort of neglect the many parameters that may not be directly relevant to your question, quite often the system is still very complicated to analyze. So you end up having to resort to the study of benchmark scenarios, for example, or maybe sometimes some people are strong enough to just try to do brute force scans. But in any case, if you are interested, for example, in the presentation of experimental results, you really need, for practical reasons, to reduce drastically the parameter space. And this very often is not done in a well motivated manner other than to simplify the logistics of the problem. Nevertheless, one can still learn things by doing this, or this is just one point I want to make. For example, one may learn that in one of those simplifications, doesn't matter the details, when you're thinking about dark matter, you may end up having to look for special situations, even though at first sight, in a model like this, you have the 0th order ingredients to have a good dark matter candidate, like the correct interactions, the correct cross-section, masses, and so on. When you do it in detail, it may be that you really need some special situation, like, for example, having certain states being somewhat degenerate, or being able to annihilate resonantly through some particular state, things like that. So these complicated UV models illustrate that kind of a possibility. Now, there is a more practical approach, which goes under the name of simplified models. And the idea here is to keep only the relevant degrees of freedom, hopefully few degrees of freedom, and therefore have a manageable number of parameters. But the idea of this approach is that you can treat that in a consistent way. In other words, in a well-defined field theory. That's just to contrast to other ways in which you can think to parameterize your things in a more phenomenological way, which may not be as consistent as this approach. So this is a reasonably good way to present the experimental information. And here I am showing just for illustration, a particular example of that. You could imagine a simplified model where you keep only a mediator, which is here called a Z prime. So it has some sort of interactions to the standard model, the quarks in particular, with some coupling GQ, and also interacts with a dark matter particle through a coupling GDM. And the process, of course, can happen either in the S channel, which is relevant, for example, for at colliders, or a T channel like this, which might also be relevant in direct detection. So basically, you have focused now your study on a much simpler model, which 2 new degrees of freedom, and basically 2 additional parameters, couplings, plus these 2 masses, the mediator and the dark matter mass. And so that's something that it's easier to deal with, and to, even though it's still 4 parameters, is quite a bit, but okay, it can be done. So in fact, colliders are primarily mediator discovery machines, in the sense that you get tighter constraints on the mediator mass than on the dark matter mass, okay? And there are different types of mediators. Let me just distinguish 2 broad categories. One could be non-mediators, so something like that we know exists, for example, the Higgs boson, and that's something called the Higgs portal. Or they could be exotic mediators, something new, as, for example, happens in supersymmetric theories, or let's say in this Z-prime simplified model that I had before would be an example of that as well. So this would be a simplified version of something like some degrees of freedom that appear in supersymmetry, although often, so this one uses this supersymmetric notation to signify things that are not necessarily supersymmetry, but okay, it's just notation. There is one more simplification one can consider, which is the possibility of approaching the problem from an effective theory point of view. And the idea here is that if it happens that the mediator is sufficiently heavy, then we can integrate it out and obtain an effective interaction that characterizes the processes. And the appeal of this will be that it allows you to do, or in principle would allow you to do an analysis in a somewhat more model-independent way, because you are not putting in fully the details of this mediator. So again, just to give this example, if we start with the previous situation of the simplified model where you exchange a spin 1 field, but it is heavy, then you end up with a contact term involving the 2 dark matter particles and the 2 standard model particles, which I'm calling psi here. and some coefficient here. If I'm imagining that this guy is a fermion, that would have a mass of dimensions of 1 over mass squared, which is given in terms of the fundamental properties originally like this. So 1 over lambda squared, the scale is given by the mass of the mediator, but there are these couplings here that appear in the vertices. And this operator here I'm writing schematically. There are different structures you can write, and the details of that of those operators carry information about the underlying mediator. So you can classify the types of operators, and based on that, try to get information, as much information as possible, in a way that doesn't necessarily assume what kind of mediator you have, but that you could apply to a particular case if you were interested in. So this just to illustrate of a few, there are more, but a few types of interactions that arise quite often, and in particular you will see when you look at the analysis presented by the LHC collaborations. You have the possibility of a scalar exchange. So the mediator is a scalar, in which case you get the kind of operator I wrote before. It can also be a pseudoscalar. So here pseudoscalar refers, remember, to its transformation properties under parity. And in this context, so here there is an assumption already that these guys are fermions, I already said. So there is a gamma 5, Dirac gamma 5 matrix there that accounts for this pseudo-scalar nature. If it's a vector, then you get gamma mu's here. It can also be an axial vector where you have an additional gamma 5. And the consequence of these different particles are different. So, for example, when you think about the spin, how the spin is described in these different structures, it's different. And one last example called the tensor would be something like this. Now the use of such effective terms is actually quite justified if you're thinking in a low energy environment. For example, for direct detection, you are talking about, so the energy scales that you're talking about is the energy that you expect from the dark matter particles there, which is, these are non-relativistic particles. We expect them to have velocities of the order, say, 10 to the minus 3 times the speed of light, or say a couple hundred kilometers per second. So these are really low energies and typically much lower than mediators masses you may have in mind. So this is quite justified in a case like that. This approach of effective theories has also been used at the LHC to derive bounds on this scale lambda. In that situation, perhaps not surprisingly, the bounds are of the same order as the available energies that we have there, say 100 to GeV to 1 TeV. And in that case, you have to be a bit careful, okay, with this approach. So one thing to notice is that the coefficient in front of the operator depends on this, or some particular combination of the fundamental parameters of whatever model this arose from. And okay, there was, I don't know what happened here, but so let's think about different possibilities here. So what I meant to write here is if this coupling lambda dm is of order 1, or both of order 1, then the scale lambda here will be of order this mass of the mediator. And that means that since you're putting a bound of that order, which means you're exploring the physics with energies of that order, that means that you should be able to produce that state and you shouldn't have integrated it out. So this interpretation in that context, done naively like this, would not be self-consistent. On the other hand, if this lambda dm is of order 4 pi, so kind of large, some sort of strong coupling setup, you can have that lambda, this scale here, that's what I meant here, can be smaller than the mediation scale. So you can have some hierarchy between the mass of the states you're producing and the scales you're exploring. And in a case like that, the effective field theory approach could be justified. And in addition, notice that when you're talking about a strong coupling model, the simplified model approach may not be useful, because that's sort of a part of the deal there is that, okay, you simplify your things, but then you also hope to be able to do perturbative computations in that setup. And that may not be the case if you have something in mind like that. And remember that one of the things we don't know is if the dark matter particles have self-interactions, so that's as distinct from the interactions with us. And in fact, the bounds one can infer, say, from studies of the, say, bullet cluster, allow for relatively strong interactions. So it's a possibility. On the other hand, nature may be significantly more complex than naively imagined. So for example, one can have a situation like this. So this is a particular implementation that illustrates what are called hidden valleys. So you could have something like this. This is the world consists of, in some sense, two worlds. Our world, the observable sector, which is this red, so this denotes the spectrum, so these are different states of different masses. And another world, which is a dark sector, which, why not? It could be quite rich as the standard model. The observable sector, here I'm using the word in a somewhat extended sense, so this I'm thinking of a supersymmetric scenario where there is the standard model sector that we have seen, and there is a super partner sector which is heavier than that, and perhaps that's why we have not seen it yet. But it could be the case that at the LHC, it's easier to access these states, but then those can sort of go through this dark sector and do something there, so produce these particles, they decay and so on, and eventually they come back to the standard model sector, and you would see some signal. Okay? So again, we don't know, but this is just to illustrate that as far as we know, things could be quite complicated. And as I said, based on what we know about the complexity of the standard model, it is not necessarily a far-fetched idea. So we have many ideas, theoretical ideas. Many of those often have something to do with dark matter. But there are still many ideas that will have different implications for dark matter. And then we also have a classification in terms of how to approach the thing from a practical point of view, going from more complete models through simplified models of different types where you drastically reduce the number of degrees of freedom, to, if you can justify it, the use of effective theories. Any questions? Okay, so let me turn to the question of the collider dark matter search strategies. So here, the important concept is that of missing energy. So remember that in a machine like the LHC, where you're colliding proton beam against proton beam, this is actually quite a complicated initial state, since the proton itself is complicated. And at these energies, when you have some collision, the collision really happens between the partons, the constituents of the proton. And in particular, that means that we don't have exact knowledge of what is the longitudinal momentum carried by these partons. So you should forget about thinking about the longitudinal momentum and concentrate on what happens on the transverse plane. And in particular, you can consider the concept of missing transfer energy. Namely, you see some event where you see some particles going in some direction, but when you add up the momenta in the transverse plane, they don't add up to zero. So naively, momentum will not be conserved, but we trust momentum conservation enough to allow us to infer that there's actually something that we are not seeing and is carrying this missing momentum. So basically, the missing ET is the negative of these observed momenta. And so that's an important observable that is relevant in the case of dark matter, since if you have produced dark matter, and so as I said already, it doesn't interact electrically or strongly, it has to interact sufficiently weakly, you expect, like neutrinos, that it will leave the detector, and you will not see it. But so you can see it by looking at missing ET. In this context of the dark matter searches at the LHC, you can distinguish two broad categories. One is when the dark matter particle appears in the final state. So that's the most direct way you would think you would look for dark matter. But you can also consider cases where the dark matter particle does not appear in the final state. And this is connected to this concept of the mediator that I mentioned before, because if there is some situation like that, so you have a mediator that couples to the standard model, it can go back to the standard model directly instead of dark matter, and you can hope to see some signal connected to that. And that will give you a handle to this new sector that is connected in some way to the dark matter. Now, how do you see the invisible? Let's think of the first category. If you produce dark matter particles, if that's the only thing you produce, yes, please. No, so the missing energy is by definition only the transverse plane. So if you see, so you're not looking at all at the longitudinal part. So, you're talking about other sources of. Oh yes, right. So dark matter is not the only way in which you can have missing energy events, right? So the concept, okay. Experimentalists look for this thing in practice all the time. It's used all the time, for example, to infer the presence of neutrinos. So what you have to do, the strategy always is to compare to the standard model expectations and see if you can see some, let's say, some excess, more events of certain type that cannot be explained by events that produce neutrinos, for example. So you have to compare. Okay, is that your question? Maybe I misunderstood. Okay. So I was saying that if you produce only the dark matter particles chi-chi, you will not know about it, right? Because you produce those, they just go away and you never learn that they were produced. So you need something else to tell that something interesting happens. And the trick here is to remember that there is the possibility of what people call initial state radiation, ISR. So, for example, you can radiate a gluon from the initial quark or anti-quark. And this will produce a jet at the LHC. So an event like this, you would see only one jet, which clearly will not conserve momentum, carries momentum in some direction. And there is probably something going in the opposite direction. You can consider not only jets, but you can consider other possibilities like photons or the W or Z gauge bosons, the Higgs. And those can be used to tag the event as something interesting. And in fact, so these are generally called mono X searches. But nowadays, people do look at cases with higher multiplicities. In other words, where the X here, like the gluon here is not only one, but could be several, like several jets or top pairs, for example. But still, at least for the moment, one, without being too careful, one calls this mono X searches. But just keep in mind that they can be a bit more general than this. If you assume that, so what do you mean by assume? So what, dark matter here means missing ET, right? So right. So typically, so the cases where these mono X searches are applied are, which actually I'm going to just let me make this statement. So cases where the dark matter particle is light compared to the mediator, So you produce the mediator, and it produces, let's say, a pair of dark matter particles. They will be highly boosted, right? So we'll go into that direction. And then that configuration, we will have the jet in the opposite direction. So I don't see there in that. So I don't know if you're imagining a case where the missing energy is sort of. So there's enough complication with the jets that the missing energy can be on top of one jet or something like that. Anyway, I don't know what would be the answer to this question, but. Okay, so this situation is the classic mono-X configuration. Of course, you can also think about other possibilities, like this more traditional missing ET plus anything, sort of SUSY-like searches, or the searches for resonances, such as the jets, that can be recast as searches for the mediator. So let me go over a few plots just to illustrate what we have now. So there's a plethora of searches that have been carried out by both the CMS and Atlas collaborations. So for example here, just for illustrations, we have a monophoton search. And so something you should keep in mind is that these results are present. There are some assumptions here. So they will clearly state, for example, here, they're assuming that it's a vector exchange. The mediator is a vector, and the dark matter particle is a Dirac fermion. So it's a particular type of simplified model they're using to interpret these results. And they also assumed something for this plot about the couplings that are involved in this simplified model. It turns out that there is some standardization of when you need to choose values, what values to choose so that you can compare things between experiments. But anyway, so you see here that, so this is the mediator dark matter mass plane, which is a typical way to present the results. And one can see, for example, here what I was saying earlier, that so if you look at these various curves, the bounds on the mediator mass are stronger than those on the dark matter mass. You can also look for Higgses. Here I put somewhere, so I added the diagrams just to have an idea of what the kind of process one has. So this is some sort of Z-prime simplified model. Again, similar situation qualitatively compared to the previous one, but of course a very different signal. This is the case where you allow the Higgs to decay into a bottom pair. You can even look at monotopes in a diagram like this, where you produce a top together with the dark matter particle through some scalar exchange. And so you have here the bound, the expectation in this particular theory. And for instance, in this particular case, you can infer a pretty strong bound on the mediator mass, this phi particle, the scalar, in the multi-TV region. We can also consider, let's say, di-X searches. So for example, an important one is the case of di-jet. So this falls into the second category I was mentioning, where you do not produce dark matter particles in the final state, but rather you produce the mediator, which then decays back into, let's say, quarks and produces two jets. And what you would see here is, if it's there, would be a bump. It's a resonance. So you're looking directly for the mediator, and that allows you to set this kind of bounds. So here, this is shown from Atlas. So they show the coupling of that mediator to the quarks and the mass of the mediator. Some tricky things in these cases is that because you produce many jets, there are many ways to produce jets at the LHC. There are large backgrounds, and that means you end up having to impose aggressive cuts that basically require your jets to be sufficiently energetic, and that can hinder your ability to look into the smaller mass regions. So these things, even though they make an effort to extend it down to a few hundred GeV in mass, it's not easy to go below that. And that means in particular, for example, that existing bounds from other experiments, say at Fermilab at the Tevatron, can still provide, or Lepto, can still provide the strongest constraints in those lower mass regions. So it's not the case that our latest machine, the LHC, supersedes previous results. It ends up proving a complementary region. You can also have interesting studies like this, producing two tops in addition to so plus missing ET, so you have dark matter. And okay, so this is just one way, again, you can present the results, the mass of the mediator versus the coupling, the relevant coupling here. And so you can study that and put some bounds. And this is, again, just to illustrate the point that in the mediator mass, dark matter mass plane, you can have, okay, this is a case where you constrain the mediator mass, say, up to 2 TeV, but basically there are, well, no constraints on the dark matter mass. Now, there is also the question of how to connect whatever information you get at colliders to other searches. Because one would like to translate, if possible, those findings into what are their implications for other searches, let's say direct or indirect detection searches. And doing this in a generic way, model-independent way, is not really feasible. It's just that the relevant issues at play in these different setups are just different. But within a given model, one can have better defined connections. And so given some assumptions, which, okay, as long as you state explicitly is okay, then you can try to translate whatever you find, say, at the LHC into what it implies in other setups. And this is something that is done nowadays. But so again, to stress, one should be aware when one look at such interpretations of the model dependence that is there. And a bit more generically, this also means that establishing a final picture, if we were to have some positive signals, will really require all of this information in addition to theoretical considerations. Okay. So let me start with this. This is a somewhat older plot, but just to, it shows clearly a simple point. When you do this exercise to compare to direct detection. So basically, okay, this is a CMS search. They say it's a bit old. I'm going to show you the latest plots next. Some particular model. And given this model and the bounds you put from the LHC, you can translate in what they imply if you imagine that this is what's going on in a direct detection experiment. And so you write this in this standard plane for direct detection, where you plot on the vertical axis the nucleon dark matter cross-section versus the dark matter mass. And the thing to see here is that, so this red line would be the bound derived from the LHC study, as compared to other to direct detection experiments, such as xenon here, which is the strongest. It was the strongest at the time. Now we have xenon 1 ton, but okay. But this shows the general lesson, which is that whereas direct detection experiments become insensitive when the mass of the chi particle, the dark matter particles, becomes too light, below several GeV, the sensitivity of the LHC result does not depend on that. And as a result, you can infer something that could be interesting in this lower mass region. Still, in the higher mass region, typically the direct detection searches end up putting stronger bounds on this. But one should keep in mind that this is still important even in this region, because remember that these kind of bounds have other assumptions, such as coming from astrophysics, which are not here. So in that sense, this is still complementary. remember also that in the context of direct detection, you can consider the possibility of nucleon dark matter interactions which are spin dependent or spin independent. And because you're dealing with heavy nuclei that contain many nucleons, many protons and neutrons, then when you're talking about spin independent cross sections, you get an enhancement factor due to the multiplicity of these states, whereas this doesn't happen for the spin independent case. So there is an important difference in the direct detection searches depending on whether your interactions are dominated by spin dependent or spin independent type of interactions. But at the LHC, this doesn't make so much of a difference. And so just to illustrate, so this is a similar plot translated into this cross-section versus dark matter plane. And this would be a monojet result, which, by the way, gives the most sensitivity at the LHC in this type of searches. And so we have here from CMS the case of a spin-independent cross-section, and from Atlas, the spin-dependent one. But the bounds from the LHC are kind of similar. However, as I said, because the direct searches for that focus on spin-independent versus spin-dependent make a difference, then what you find is that in the spin-dependent case, these bounds can be easily stronger than those from direct detection experiments in a much larger mass range. Okay, let me skip this. We can also try to compare to indirect detection. So this is an example, again, by CMS, again monojet, where so they translate now. So this is a particular model, again, as I said, so illustrated by this diagram. So you produce here your jet. And in the dark matter mass plane, you can, in the dark matter, so the horizontal axis is dark matter mass. And in the vertical axis, you have translated this information into the annihilation cross-section times velocity averaged, which is relevant for indirect detection. And then you can put on top of that the bounds that are inferred, for example, by the Fermi-Lat collaboration. Those bounds depend on the, remember what you're doing there is you are waiting for the dark matter to annihilate into standard model states, which end up producing along the decay chain photons that can be seen by Fermi-Lat. And exactly what you see will depend on how the dark matter annihilates. So they make some simple assumptions again there. In the case of this simplified model, those assumptions are kind of clear. Basically, you are imagining a situation where if you read this diagram, forget the jet here, which is just for collider purposes, but if you read the diagram from right to left, you're basically annihilating into, in this case, up quarks. And that's what this, the assumption behind this curve. So in any case, so this illustrates that the comparison that you can make between these cases and how, given these assumptions, you can infer strong bounds. Now, going a bit more detail about these comparisons, as I said, there are different types of mediators for like vector, axial vector, scalar, pseudoscalar, and those things make a difference. So just to compare direct detection and colliders, for example, if you're talking about the vector, the direct detection experiments are more sensitive than colliders, except perhaps in this low mass region. So for example, the very naive expectation that when you say that if you're talking about a WIMP, a weakly interacting massive particle, and if you were to interpret that literally as something interacting with the Z-gauge boson, or W perhaps, as we know ours do, that's a region that has been tested already in direct experiments, and so it's not there. So it has to be a bit more complicated than that. But okay, that's just a simple-minded interpretation of those words, weakly interacting. If instead you're talking about an axial vector, where you have this gamma 5, it turns out that the direct detection and colliders are about equally sensitive, but in different regions of parameter space. And similarly for scalar and pseudoscalars, you can make some statements. In particular, the case of the pseudoscalar is one where there are no limits from direct detection and only from indirect. But colliders can provide limits which are comparable to the scalar couplings. So this again illustrates how looking at this from this additional angle gives complementary information. More generally, I already said this, but okay, so if we compare colliders versus direct or indirect, the colliders tend to be more sensitive in the small mass region, which means 1 to several GeV, and less sensitive in the intermediate and high mass regions. On the other hand, the direct detection depends strongly on the structure of interactions, say the spin-dependent versus spin-independent structure, and that ends up giving an edge to the collider interpretation in the spin-dependent case. In the direct detection case, also there is a strong dependence on the detector technology, so what kind of material you use, for example. For indirect detection, you have a dependence on astrophysics and also on the annihilation channels. So anyway, this goes back to this complementarity concept where you would like to use all this information together to end up putting a picture at the end. One more topic. So I have 10 minutes because there is an important eclipse to be seen now, so very mystic. So there's a sharp cutoff. So just a word about invisible Higgs decays. So this is one of the possibilities I mentioned earlier in the classification. You could have a mediator which is a known particle. And an obvious candidate for that is the Higgs boson, which could talk directly to a dark matter particle. So okay, again, you have to make assumptions. So for example, if you imagine that the dark matter particle is only one, this chi here, say, it's also a standard model singlet, which is coupled to the Higgs. That in addition, it's really the mediator for the WIMP nuclear interaction, and that it is light enough, meaning that it's lighter than half the Higgs mass, which means that the Higgs can decay into two dark matter particles, as shown in this diagram. Then you can again translate this into this plane, the WIMP mass versus WIMP nucleon cross-section. And depending on the character of the dark matter particle, scalar, fermion, vector, infer different bounds. Anyway, so it's an interesting case where you're using very recently discovered physics, the Higgs, to learn something about such things. And the last subject I want to treat is that of light mediators. The thing here is that, so maybe you noticed in the previous recasting of LHC results in the cross-section versus mass plane, you could access masses down to about 1 GeV, but they don't show more than that. And the reason has to do with important backgrounds that don't make it feasible below that. But you can certainly imagine cases where the mediator is lighter and even have motivations for that. And so this, okay, just very quickly, remember for direct detection, the relevant energy transfer is basically set by the velocity of the dark matter particles, which we can estimate. So it's a non-relativistic particle. We say it has a velocity of 10 to the minus 3 times c. And so that gives us, if we put a mass in the multi-GeV region, this kV scale, which is basically, it's of the order of the thresholds that you have in those detectors. So that's the kind of recoil energies that you can see. So as I said, the collider searches can extend this multi-GeV down to 1 GeV, but not below that. So you can ask, can we go that? And the answer is yes. And you can do it with a collider experiment. So for example, I have been emphasizing the ATLAS and CMS collaborations at the LHC because they have done the most studies. But there are other experiments. So LHCb has done studies that have implications for dark matter. There's also the so-called B factories that can also say something. and other experiments called beam dump experiments that I don't have time to describe, but you can ask me if you want. And one example of this is what are called dark photons. So this is the idea where you have a new U1 gauge field which mixes to hypercharge. So you have some Lagrange like this, or this F prime. If you see, there should be a prime. Okay, this dot was a prime. And it's massive, and there is this sort of kinetic mixing with the hypercharged gauge boson. And basically, intuitively, this allows you to start with a photon and convert into a dark photon, which then allows you to connect our sector to some dark sector. So in fact, in that context, so the parameters are this epsilon parameter, which is this epsilon is the parameterizes this mixing, versus the mass of the A prime. And we see, so there are many types of experiments that can put constraints on that. I will not go in any detail over this, but some of the experiments I was mentioning, they can fill some of these part of parameter space, which is interesting. And even at higher energy, so note that these experiments that have something to tell in the region of masses below 10 GeV, but even at higher energies, and even considering like 100 TeV collider, they can fill in some of this parameter space in some region in this plane. So there is something to be learned here. Now there are some further topics of interest that I haven't mentioned, just for lack of time. But if you're interested, you should take a look. So generally, there are many searches that bear on the question of dark matter. There are also other possibilities, for example, super weakly interacting dark matter, such as gravitinos. You can also consider more exotic physics motivated by dark sectors, long-lived particles, particle searches, and I mentioned also these axion searches, which require different techniques, not collider. So we'll just end up, I put some references here in case you want to explore this further. Thank you.
So we have time for, let's say, 2 questions before we go for the eclipse.
I was wondering what was the main background for monoshed searches for mono-X?
I just, let me see the main. Yeah, don't remember exactly what's the main background, but you can so you can. So
you can reduce it with cuts, but I was wondering what was the...
So I don't remember, so I don't know what was that's the main one, but so you can consider, for example, the production of, let's say, 2 Zs, one of them decaying into jets, that would be your, which are, so it's boosted is one jet, and the other one decaying invisibly into neutrinos. So there are several backgrounds. So what you do is, okay, you compute those, and you try to see an excess over that.
Another question? Okay, just recall that Professor Eduardo is from here, so he will be here next week, and you can look after him to make more questions. Maybe we will find a way to have some discussion, some question sessions next week. Next week will be tight. So just some comments. Sorry for cutting short the coffee break, which meant that the poster session was cut short too. But the posters will be exhibited there next week. So every poster presenter will have the opportunity to present the poster next week and to discuss. Good news, 3 experiments that are already here are working. You don't have an idea of how much hard it was to make it work. You haven't seen the co-chair Carla here often because she was making that work, but 3 of them are working. A lot of are here. The rest is coming this weekend. So in principle, Monday, all the 10 experiments should be working. People will be working the weekend for that. The rooms of each of the experiments are already assigned, but the persons and the times, the days and the people that will do each experiment are not assigned yet. So you have that information on Monday.
I am very impressed. This is a theory institute. It shouldn't work.
Well, I think some will not work. It's just a probability, but let's hope they will. But some are working already, so that's good. Recall that next week classes restart in schools, universities, so I guess the metro will be more packed. There will be more people around, so plan ahead of time, Plan to arrive 1 hour earlier than this week, half an hour earlier, and then if you get too early, the next day you can, but do plan earlier next week. And, I'm not from São Paulo, so I cannot give many recommendations. I know this is a wonderful city with a lot of options for the weekend, so enjoy São Paulo, and thanks a lot for this first week of participation, and we look forward for next week. Let's thank again Eduardo.